Hello students, I'm going to take you through a few of the answers to the NMR practice exercises. For A, looks like we have propane with 2 chlorines on it. If you look at this particular structure, right, you notice that there's only 2 signals and we have 3 carbons. That suggests that there's some symmetry here, right? Symmetry might suggest the 1,3 dichloro, where there are 4 hydrogens here, and here, and 2 hydrogens here and here. The 4 on the 1 and 3 position are actually going to be these right here, right? Look at the chemical shift between 3 and 4, indicates a chlorine. Look at this integration. This integration is twice as big as this one. And if you have 6 hydrogens total, that implies that this is 4 and this is only 2, and the splittings also match up, right? So the ones I've circled are these right here. We'll call that group A. And the 2 hydrogens I didn't circle are over here. They have 4 neighbors, leading to a quintet. Over here in B, this is of course what ethanol looks like. There's only 2 possibilities for C2H6O. You know that it's saturated. This right here is a puzzle, right? So what is this, right? At first glance, this looks like a quartet, but we know it really can't be a quartet, right? Because a real quartet is a 1-3-3-1, and this one is super big. So this is a singlet that's on top of a quartet. A singlet usually indicates, or not always, but often indicates an alcohol. So this is the alcohol. These are the 2 hydrogens on the same carbon as the alcohol, and this is the 3 hydrogens in the CH3 group, right? So ethanol. The integrations match that too, right? So this is a total of 3. This is a total of 3. And of course, one of those is that alcohol one. If you look at this one, this was from your isomers of C3H5Cl3. This is the 1,1,2 isomer. So propane, there is 2 chlorines here, Cl, 1 chlorine here. So the hydrogen here is next to 2 chlorines. That would, of course, be this one. The hydrogen here, right, also only 1. This one has a bunch of neighbors, right, like 4 neighbors. That gives you a quintet. Notice this integration is the same as this integration. So 1 hydrogen, 1 hydrogen. And then these, of course, are all 3 of these over here. So all 3 of these over here are the ones over here. They have 1 neighbor, so they're split into a doublet. Check out that integration, much bigger. Chemical shift also below 2. 4C, this one is propanal, like this. This one has a very characteristic chemical shift, almost always between 9 and 10. So that one is here. This piece is a little funky, right? So you notice that this one technically should have 3 neighbors here, plus this one here is a 4th neighbor. So this technically should have 5 neighbors. Instead of that, we only see a quartet. But if you look close, you see some tip splitting here. I'll zoom in on that just a little bit. The tip splitting here tells you that there's a double bond nearby, that there's a different kind of neighbor. So we'll talk more about that in class soon. But you know, if you look at the structure, if you look at the formula, this is the only sort of possibility with an aldehyde. So these 2 are these 2, right, between 2 and 3. And of course, this integrates to 3 hydrogens. It's way, way, way upfield around 1. It has 2 neighbors making the triplet. So these 3 are these 3. This one, oh my goodness, only 1 peak. This must have a lot of symmetry and no neighbors. The way you get that is with propanone. So all 6 hydrogens, 3 here and 3 here, are all magnetically equivalent. They all have no neighbors. If you look at the chemical shift, that's the carbonyl compound chemical shift. You see that between 2 and 3. That's the only way you can get all that magnetic equivalence. Notice lots of symmetry here. For this one, out here, anytime you have a signal above 11, that's screaming carboxylic acid. So we know we must have carboxylic acid. And this hydrogen on the very end is this one above 11. And we also know we have an extra O here someplace. And notice there's no splitting anywhere here. So we have to somehow separate those remaining hydrogens. And this is the way that you do that. So these two right here are these. They have the chemical shift that's bigger than either an ether or an acid because they're sandwiched in between. And these three right here, notice three of them have a bigger chemical shift. So that would be this last group over here. And that one has chemical shift indicative of ether. Oh, this one is a mess, but check it out. I go for the easy ones first. Between 9 and 10 indicates an aldehyde. So I'm going to go ahead and put in that aldehyde like so. And one of the things I notice is I have three O's, right? If you ignore O, what you see is C3H6. So that indicates 1 degree of unsaturation. I already have my degree of unsaturation, right? I already have the double bond here. So everything else is saturated, which means if there's oxygens and they're saturated, that only leaves alcohols and ethers. Ethers would separate these things out like this one above and give you something that looks more like this, right? C3H6O3, C3H6O3. So I'm going to try some alcohols, right? First of all, I see this is a singlet. It looks like an alcohol. Also this, right? At first glance, this between 3 and 4 might be a triplet. But remember, a triplet is a 1 to 2 to 1 ratio. And there's a little funny gap here. So this is actually not a triplet. This is two signals. That's an alcohol and that's an alcohol too. If you look at the integration, what you see is that this is one hydrogen. We know that because it's this one right here. This is twice as big, and it's two signals, one of which we think might be an alcohol, and the other of which has some neighbors down here. And this is 3 hydrogens, right? So if you do the math, so this is 1 for the alcohol and 2 here. That suggests a structure that looks something like this. There we go. So these 2 hydrogens here would be these 2 right here. The 1 hydrogen right here is going to be this right here. And then we don't know which is which, but this makes one singlet, maybe this one. And this makes the other singlet, maybe this one. Actually, because this one is near the aldehyde too, maybe our best guess is that this one is this one. And this one is this one. But we really can't tell. The alcohols are sometimes weird. So for H, oh my goodness, lots and lots and lots of hydrogens, no neighbors. Also, if you ignore the O, we have CnH2n plus 2, which means we're saturated. So no double bonds and no rings. So the way oftentimes that we get no neighbors at all is with a quaternary carbon. So look, these are way, way, way upfield near 1. So CH3, CH3, CH3. There's 9 total hydrogens here. Those are all these right here. Right? We know there's an O, which makes us think either ether or alcohol. In this particular case, alcohol seems to fit. So the 2 hydrogens here are these. Right? Notice between 3.4 and 4 fits an alcohol chemical shift. This is that hydroxylic one. That can be anywhere, but a little teeny peak oftentimes is indicative of an alcohol. So these 2 are these 2, and all 9 of these suckers are all magnetically equivalent. That's that one. Oh my goodness. Above 10 suggests acid. So I'm going to go with carboxylic acid. Good. Notice there's also an extra O, and the rest is saturated. So again, it suggests either alcohol or ether. This singlet maybe suggests that there's an alcohol someplace. If you play around with this, right, you can either put the alcohol here or here. If you put it here, the remaining hydrogens are going to have 1 here and 3 here. These look like they're equal to each other. So I think actually if we put the alcohol here, this one is this one. And then I have 2 hydrogens here and 2 hydrogens here, each with 2 neighbors. So one is this one and one is this one. Which one is which? That's actually pretty tricky. If you look at like hydrogens near an alcohol, they actually clock in usually between 3.4 and 4. Hydrogens near an acid like this usually clock in between 2 and 2.6. So those are actually those over there. This one, of course, is this one. All right. Oh, that one at first glance is a real head scratcher until you realize We have to practice some social distancing. That one looks like this. All 12 of these hydrogens are magnetically equivalent. They all have no neighbors because of this quaternary carbon. So that's going to give us that. This one is very interesting. Like, what's going on here? If you remember, if you look at to see if we're saturated or not, for halogens you actually have to add them in. So a halogen counts like a hydrogen. So C4H10 is the equivalent here. That would suggest saturated. This is a very characteristic structure. So first of all, notice the integration is teeny tiny, suggesting not very many hydrogens. But you look here, it's been split into a zillion peaks. We can see 1, 2, 3, 4, 5, 6, and then maybe there's even a suggestion of other ones. So lots and lots and lots and lots of neighbors, but only one hydrogen. That doesn't guarantee that it's this kind of structure. But oftentimes when you see something that looks like this, it's a hydrogen on a tertiary carbon. It's small, right? It's a small signal because there's only one hydrogen, but it's got a zillion neighbors, right? And so this actually is the structure. One of these, of course, has a chlorine. And so the hydrogens that are near the chlorine, these two are this, and the other 6 hydrogens are going to be this over here. So all 3 of these and all 3 of those are this one over here. There's a little bit of overlap or coupling here. In an ideal case, this would be a symmetrical doublet, but you see it's not. Don't stress too much about that. All right, a few more. Oh, check this out. We just talked about what this is, right? Small signal split into a bazillion pieces, and then all the rest of these are almost the same. So again, this is a tertiary carbon. That's a carbon. C. So this one is this one. This one has 9 neighbors, so you should see 10 peaks down here. You might not, right? If your spectrometer is not sensitive enough, you won't pick up all 10. But you can see, right, that they kind of like, there's almost like an asymptote, right? There's a teeny tiny one that suggests that maybe there's a smaller one that you can't see. And of course, all 9 of these are this right here, right? They all have one neighbor. Here's their one neighbor. That's why they're split in 2. Again, in an ideal case, this is a symmetrical doublet. There might be some coupling or some overlap here. And M, right, signal, here's another super characteristic thing. When you see something between 7 and 8, not always, but many times, especially if it's a big signal, that's going to be benzene. And C6H6, lots of unsaturation there, all equivalent, which suggests some magnetic equivalence. So that one is benzene. I hope this helped. If you have more questions, pop by and see me during office hours. Take care.